Now we know that all matter is made of atoms, so from now on, for my own convenience, if I don't show any charge inside of an object, you can just assume it's neutral. Neutral objects make up most of our world as we know it, but they're not that interesting. Charged objects are more interesting. Positively charged objects are created by removing electrons from individual atoms within those objects to make ions. So when we have an object that looks like this, what it really means is that there are 2 units of positive charge in a sea of atoms. Similarly, we can create a negatively charged object by adding electrons. What we got here is an object with 2 units of dangling negative charge. Now, I'm going to propose to you a really interesting idea, a way of creating a charged object seemingly for free. The thing is, in order for this to work, we need to have an object that's already charged. What if we have a negatively charged object and we want to make another object positively charged? Is there a way to do that? Is it even possible? You might be thinking, no, of course there's no way to do that because the best we can do is touch the negatively charged object to the other object, but now all that's going to happen is electrons will flow from the original negatively charged object to the other object, and we're left with 2 negatively charged objects, not one negative and one positive. Why would the electrons want to redistribute themselves in this way in the first place? Well, we already went over the fact that electrons repel each other. They're negatively charged, so they hate each other, but they love their friends, the protons. So if electrons really do repel each other, then now we have this pathway for electrons to travel from one object to the other. So in a sense, they want to be as far away from each other as possible because they're forcing each other apart. This is a bit of a hand-wavy argument, but anyway, back to my idea. I think we can make a positively charged object using only this negatively charged object and one other resource. That other resource is the ground. The ground holds in our eyes an endless amount of positive and negative charges, so much that as soon as one of these objects is allowed to touch the ground, or the earth, it becomes neutral, because the earth allows this net negative charge to propagate itself freely and spread the individual charges so far away from each other that this original object becomes effectively neutral. Charges are being shuffled around all the time over such a humongous area that is the earth, that we might as well treat the earth as this giant reservoir that we can use to neutralize objects. So anytime we want to neutralize an object, all we have to do is touch the object to the earth, or connect it to the earth via a grounding wire. But there are a few problems with the arguments that I've just made here. One problem is that almost everything is in some way touching the earth, isn't it? So forget positive and negative, how can anything on the ground maintain any significant net charge? Let's think about something else real quick. What's stopping, for example, a charged cloud from neutralizing is the air in between the cloud and the ground. This air is what we call an insulator. Materials can be conductors, insulators, or semiconductors. Conductors, like metals, allow electrons to flow freely through them. Some of the electrons in the metal are loosely connected with their atoms and can freely flow around. Insulators like air, however, are the opposite. A pure insulator does not allow charge to flow freely through it. Each electron is stuck to its respective atom, so to speak. Semiconductors are a bit weird, and maybe we'll talk about them some other day, but a weak definition of them is that they're kind of in between conductors and insulators. They allow charge to flow under some conditions. So if you want an object to maintain its charge, all you have to do is make sure there's an insulator between it and the ground. Charge can't freely flow through an insulator, so the charged object should be safe from being neutralized. In reality, however, there is no such thing as a perfect insulator. Air is pretty good, but under extreme circumstances, even it can't prevent the flow of charge. We'll see how to quantify this property much later. Now, we keep getting sidetracked. Back to the original idea, what we want to do is take this negatively charged object and use it to somehow turn this other neutral object into a positively charged object. We can do this by using this process called induction. The way it works is you take this negatively charged object and you don't touch the other object, but you bring it close to the other object. Close enough that enough of the electrons in the other object are repelled by the negative object, and they move over to the other side. Once that happens, then you're left with a net negative charge on the right side, and a net positive charge on the left side of the neutral object. So now what if we connect the right side of the object to the ground? In doing so, we neutralize only the right side of the object. The electrons are repelling each other too much, and they can spread way farther out in the ground, so that's where they want to go. The left side doesn't want any electrons anyway, since they'd be repelled by the negative object. Once we remove the grounding, we're left with a net positive left side of the object and a net neutral right side of the object. So in the whole, what we're left with is a positively charged object. All we have to do now is move the negative object away, and the electrons will redistribute themselves. Like I said, this process is called induction, and it's an ingenious way of creating objects of opposite charge. We started out with only a negative object and a neutral object, and ended up with a negative object and a positive object in the process. I want to mention one other important thing about insulators. While electrons might be tightly bound to their atoms in insulators, that doesn't mean that the molecules themselves can't twist around in weird ways. For instance, consider the water molecule, which we commonly refer to as H2O. The molecule consists of 2 hydrogen atoms and 1 oxygen atom. Electrons spend more time on average close to the oxygen atom than the hydrogen atom, so that makes this molecule a dipole. A dipole is just a molecule that's actually neutral as a whole, but equal amounts of positive and negative charge are somehow concentrated away from each other. Water isn't the only molecule that's a dipole. Many other molecules are dipoles as well. So if you bring a charged object near an insulator with randomly oriented dipoles, the molecules inside of the insulator try to realign themselves, since the positive end of the dipole is repelled by the charged object and the negative end of the dipole is attracted to the charged object. So you can end up with a charged object being attracted to a neutral object in this way, even if it's an insulator.